morning and welcome to this press conference. Today is Chemistry Day at the Royal Swedish Academy of Sciences. We have concluded our meeting and we are ready to announce this year's Nobel Prize in Chemistry. And as usual, we'll do it both in English and in Swedish. I'm Göran Hansson, Secretary General of the Academy. With me on the podium today is to my right, Professor Sara Snogerup Linse, Chairman of the Nobel Committee for Chemistry. And on my left, Professor Olof Ramström, who is a member of the committee and an expert in the field of the prize. And later on, we hope to have one of our new Nobel laureates with us on a phone line. This year's Nobel Prize in Chemistry is about the world's smallest machines. Årets Nobelpris handlar om världens minsta maskiner. Kungliga Vetenskapsakademin har beslutat att utdela 2016 års Nobelpris i kemi gemensamt till Jean-Pierre Sauvage, Sir James Fraser Stoddard och Bernard L. Feringa för design och syntes av molekylära maskiner. The Royal Swedish Academy of Sciences has decided to award the 2016 Nobel Prize in Chemistry jointly to Jean-Pierre Sauvage, Sir James Fraser Stoddard, and Bernard L. Feringa for the design and synthesis of molecular machines. L'Académie royale de sciences de Suède a décidé ce jour d'attribuer le prix Nobel de chimie 2016 à Jean-Pierre Sauvage, Sir James Fraser Stoddard et Bernard L. Feringa pour la conception et la synthèse de machines moléculaires, für Design und Synthese molekularer Maschinen, za projektowanie i syntez molekularnych maszyn. Here we have our new Nobel laureates with us on the screen above me. And Jean-Pierre Sauvage was born in Paris in 1944. He is now Emeritus Professor at the Université de Strasbourg and Director of Research Emeritus at the Centre National de la Recherche Scientifique, CNRS, in Strasbourg in France. Sir James Fraser Stoddard was born in 1942 in Edinburgh in the United Kingdom. He is currently the Board of Trustees Professor of Chemistry at Northwestern University in Evanston, Illinois, United States. And Bernard or Ben Feringa was born in 1951 in Berger-Compascuum in the Netherlands. He is Professor of Organic Chemistry at the University of Groningen in the Netherlands. So that's our new Nobel laureates. And now I'd like to give the word to Professor Snogerup Linse, who will provide some introductory remarks on this year's Nobel Prize in Chemistry. Sara, please.
Thank you. Maybe this morning you ground your coffee. Maybe you used a motorized vehicle to get here. You used man-made machines operating on the centimeter to meter length scale. It's been the dream of scientists for over half a century to take this development all the way down to the molecular scale. That's nanometers. A nanometer is 1 million times smaller than a millimeter. In here, we have some molecular machines, a molecular motor, a molecular muscle, a molecular memory, an elevator, and there's a molecular car. This amazing development is due to several ingenious chemical innovations. A machine needs movable parts and a mechanism to convert energy input to motion in a defined direction. So the first challenge for the chemists was to make something that can move. This one you may recognize from yesterday. This one won't do the work. It's beautiful, but it needs to be connected to something. One way to make a physical connection is this, somewhat more ugly. But here we have two wings that move relative to one another, but they're freely joined. There is no chemical bond between them. To make this one is a piece of cake. You can buy it at the local supermarket. This one requires some very clever chemistry, and this year's laureates have developed new synthetic strategies to make molecules like this with good yields. The second challenge is to convert energy input to motion in a defined direction. Here, the problem is that molecular systems have a strive to reach equilibrium and fluctuate around it in random motions. So here, the challenge was to overcome this, and the laureates took advantage of a molecular property called chirality, or asymmetry. So now you may be curious to see what these machines look like. Ta-da! I'm sorry. You can't see them. They are more than 1,000 times smaller than a human hair. So we need a magnifying lens, and I think my colleague Olof Ramström can help here.
Thank you for that, and thank you, Sara. So definitely we need a magnifying lens. So as you heard, this award is all about the world's smallest machines, the world's tiniest machines. And you can actually see an example of such a machine in this little picture. This is a microscope image. And you can not only see it, you can also see it moving, as you can see here. And they are really very tiny, these structures, only a few nanometers in length. And as you heard, as a comparison, a strand of hair is more than 1,000 times thicker. So really the tiniest possible machine you can experience. So how can you make these machines? Well, as Sara very cleverly explained to you, one very important breakthrough in this area came in 1983, when Jean-Pierre Sauvage and his group made a so-called molecular chain. And the way they did this is that they constructed a molecular ring, and this is symbolized here in blue, and they had a molecular crescent-shaped molecule here in red, and you can see the chemical structures here on the sides. And when you mix those two structures together with a small copper ion, the copper ion can act as a type of glue, gluing those two pieces together in a type of complex like this. And what you then can do is that you add a third component, another red component here, you can see the structure over here, and then you can stitch them together chemically. And what you then will get after you remove them, the copper ion, is a type of molecular chain type of structure, also known as a catenane. And here you have a type of mechanical bond where the two rings can move freely relative to each other, but cannot come loose from one another. So it's a type of mechanical bond. This opened an entire field of molecular machinery, and it also reinvigorated another field, which is called topological chemistry, where you actually study very complex situations like this. What Jean-Pierre Sauvage and his group also realized at this point was that here you have what is called translational isomerism, because in the presence or in the absence of metal ion here, you have a large shift in shape in the structure, up to 1 nanometer change in shape. Another very important breakthrough in this area came in 1991, when Fraser Stoddard and his group designed a so-called molecular shuttle. They used another type of mechanical bond, which is based on an electron-rich axle like this in red here. And they also made a ring-shaped molecule, which is electron-poor, and you can see it's open here on one side, and the structures you can find down here. If you mix those two structures together in a solution, electron-rich will be attracted by electron-poor, and then you can ring-close the structure, and now you have formed a type of rotaxane structure, where you have the ring can move freely along the axle, but cannot come loose because of the two large stoppers at each end here. And this is another type of mechanical bond, as you may understand. And here what you can see also is that you have a shuttle effect, so that this ring can move between two different stations in this axle, on this axle. So you can see it can move like this. After these fundamental discoveries, what these two groups could also show is that you can actually control this movement. So in 1994, the Stoddard group could show, by building in asymmetries in the axle, that you can actually control the movement of the ring between the two stations. And this you can do, for example, by electrochemical means. In the same year, the Sauvage group can show similarly that you can build in asymmetries in the catenane rings, and by electrochemistry you can also control the movement, the rotation of one ring relative to another. After these fundamental breakthroughs, both of these groups have done a lot of work, and they have constructed more and more complex structures and more functional structures. Just to give you a couple of examples out of very many. Sauvage group have, for example, designed a molecule, constructed a molecule which can extend and contract dramatically in a very controlled manner. And this is actually mimicking the function that we see in our muscle tissue. So we can call it a type of molecular muscle. And the Stoddard group, they have done many things. One example they made was a so-called molecular elevator or lift, where you have a plane in red here that can move between two stations upon external stimulus like so. So, one component in a machine that is very, very important is the motor component, and especially maybe the rotary motor component, and in particular a component that we can rotate only in one direction. And that is a fundamental challenge, and that challenge was met in 1999 by Ben Feringa and his group. So what they could do in this particular case was that they made a molecule, they built in asymmetries in the molecule, and they had two rotor blades, as you can see here, connected to what is called an isomerizable bond, a bond that can change. And using this structure, they can get unidirectional rotation. And the way this works is that when you shine light to this molecule, the rotor blade will flip over, like so, almost 180 degrees. There you see. And that will create tension in the molecule, as you can see here. The molecule doesn't like the tension, it wants to release the tension, and that happens in the thermal step, which is irreversible, pretty much irreversible. And then you have another pulse of light coming in. You get another flip of the rotor, you create more tension, and then in the final step, you have a thermal relaxation again, and then you're back at where you started. And this cyclic moment you can do over and over again in a very unidirectional rotation manner. After this fundamental breakthrough in 1999, the Feringa group and other groups have been working continuously on this field, and they have perfected their structures even more. So nowadays they have structures that can rotate very fast, up to 12,000 revs per second. They have motors that can rotate in either direction. They can also change the direction at will if they want to. They have also worked with, they also show that you can use these molecular motors, these tiny molecular motors, to rotate much, much larger objects, as you can see here. Here you have a glass rod, and this glass rod is in micrometer size. That means it is 10,000 times larger than the little molecular motor. And as you can see, the motor action can actually be used to drive the rotation of this very large rod in comparison. And the final example I have for this from this group is a more playful example. And what they wanted to show here is they wanted to demonstrate that you can control the motion of a small machine on a surface. And what they actually did then was that they constructed a molecule where you have an axial type of structure, and in each corner of this axial they connect a motor component. So what this then will look like is some kind of four-wheel drive small molecular car. And the way they imagine this to work is you can see on this cartoon where you can see that this structure can move along the surface in this manner. And this particular machine or molecule is exactly what you see here. That's what you see the machine moving along the surface. So what these three laureates have done, they have opened this entire field of molecular machinery. And they have constructed, they have shown that it's indeed possible to make machine or machine-like function at the molecular scale. And they have really mastered motion control at the molecular scale. So now, I think you all can say that this is really fantastic, right? But what is it used for? What can it be used for? And I would like to say that this is, until now, fundamental science. This is basic fundamental science. They have addressed fundamental scientific challenges and shown that this is indeed possible. And you can say, probably you can say that the development stage here is similar to what it was in the beginning of the 19th century, when many scientists demonstrated different electrical machines, as you can see of some of them here. And of course, these electrical machines from the beginning of the 19th century, they created a revolution. And as you can see, nowadays we have electrical machines everywhere. So we think that these small molecular machines, we have seen some tendencies towards applications, but the future will show what kind of applications will come out of this. So by that, I just want to give the word back to our Secretary General.
Thank you very much, Olof. It's an exciting set of discoveries, an exciting field, isn't it? We may now have one of our new Nobel laureates with us on the phone line. Professor Feringa, are you there?
Yeah, I'm there.
Great, thanks for being with us again. This is Göran Hansson who called you.
Can you hear me?
I hear you loud and clear. Can you hear me?
Yeah.
Good. So I'm the guy who called you about an hour ago, but now I'm to give you the good news. But now I'm sitting in the session hall of the Academy, and we have journalists from all over the world here, and they are, of course, eager to ask you questions. So are you ready to take some questions?
Sure.
Great.
Of course.
Wonderful. Who would like to start? Thomas von Heine, fast as always.
This is Swedish television. Congratulations, Professor. I'd like you to tell us two things, actually. First, what did you say when you heard the message today? And then, what did you say when you saw your first functioning molecular machine several years ago, I guess?
Now, what I said when I got this message, that I said I don't know what to say, and I'm a bit shocked, because it was such a great surprise. And then my second remark was, I'm so honored, and I'm also emotional about this. Second, your second point, what I said when we saw this machine working for the first time, this was also a shock, because for the first time we saw really movement of things, and we saw that there was a kind of a motor type function. So I could hardly believe that it worked, yes. Yeah.
Thank you.
Thank you. Who's next? Yes, lady over there. You get the microphone.
I'm Annelie Megner-Arn from TV4. Congratulations on the prize.
Thank you.
And I wonder if you can imagine what your cars and elevators can be made for. Could it, for instance, be transporting medical to active sites where they do the most, where they do what they are meant for?
Yeah, you are absolutely right. It is a bit early days, of course, but once you are able to control movement, you have a motor, you can think of all kinds of functions. So indeed, we think of transporters, like in your body, there are many motors and machines that make it possible that your cells divide, that your muscles work, that there is transport in the cells. etc. But you can think also much broader. Think about nano machines, micro robots. Think about tiny robots that the doctor in the future will inject in your blood veins and that go to search for a cancer cell or are going to deliver a drug, for instance. But also smart materials, for instance, materials that can adapt, change, depending on an external signal, just like our body functions. That is the kind of functions you can think of.
Great, fascinating, isn't it? Sky's the limit. Who'd like to continue? More questions? They seem overwhelmed here by all the possibilities that open up with molecular machines.
Yeah. Let me add to that. I feel a little bit... Sorry?
Go ahead.
Congratulations to the prize. My name is Joanna Rose from Nobel Media just now.
Thank you.
I wonder what is the challenge to do now for you and your colleagues?
Yeah, now first of all, let me say I feel a little bit like the Wright brothers, who were flying 100 years ago for the first time. And then people were saying, you know, why do we need a flying machine? And now we have a Boeing 747 and an Airbus. So that is a bit how I feel. But yes, the opportunities are great, because if you think what kind of materials we can make these days with the chemistry, and when you are able to introduce dynamic functions and build machines or build materials that can change function, there is endless opportunity. So we will build smart materials in the future. That is a big opportunity. Materials that will reconfigure, that will change, that will adapt themselves, that will have properties that can change because of they pick up a signal. You can think of nanoscale energy converters. So make tiny machines that can store energy and can use that energy. And indeed, it opens up a whole new field of nano machines.
Thank you. Yes. Gentleman from Expressen. Peter.
Yes, Fredrik Lenander from Expressen. Congratulations, Professor, to the Nobel Prize and your fine achievements in the field.
Thank you very much.
Last year, one of the laureates in chemistry told us that he would spend a good amount of money on wine. What are your plans for spending the money that you won today?
Excuse me? I didn't understand your last point.
I was wondering how you're going to celebrate this fine achievement and what are you going to spend your money on?
Yeah, no, we are, of course, celebrating this with our team of all the talented young students and postdocs that have been working for all those years on this program. So I want to give all the credit to the co-workers and all the people in my team, which was fantastic, and it would not have been possible. So we certainly will celebrate with them. And we are, of course, this is the start of a new period where we are really going to try to use these tiny machines for all kinds of new applications and so.
Thank you. Please, next question.
Professor, congratulations on your prize, David Keaton from the Associated Press.
Thank you so much.
Now, obviously, the 19th century, the discoveries of the 19th century yielded the aeroplane, the drill, lots of wonderful innovations, but also some very deadly ones. This could also lead, potentially, would you imagine to, well, I'll put it another way. What are your worst nightmares with this discovery? What do you fear from your discovery?
Now, I don't know if I have really nightmares. The nice thing is about that we can design all these synthetic motors and machines and so, that we can induce all kinds of autonomous functions. So far, when we build a material, a chemical, whatever, you know, they are there, but they don't have any dynamic function or autonomous function. In the future, we have all kinds of materials that will have autonomous functions, just like a bacterial cell or so in the future. So just like a cell in your body or a bacterial cell or so. And I think we have to think about how we can handle these things safely. But I'm not so worried about that, because once we are able to design these tiny micro machines and these nano robots, we will also have the opportunity to build in all kinds of safety devices if that is needed and so. For the time being, I think we use these materials and so, and we treat them as any chemical, you know, with any if we would, for instance, use these tiny motors, and so in a biological context, they have to go through a very careful evaluation with respect to toxicity and all these things. So we are aware of these things.
Great. Yes, the lady over there.
Dear Professor, my name is Åsa Husberg, and I work in the Nobel Museum. And grattis, as we say in Swedish. Congratulations.
Thank you so much.
When did you first start to think about that I would like to make research about molecular machines? How did you come up with the idea?
Yeah, that's a very interesting point. We started, when I was in my early days of my career, I started building switches, just like Fraser, Stoddard, and Jean-Pierre Sauvage. So we could, you know, a switch, you switch between 0 and 1, just like in your a light switch. And the whole idea was to have an alternative for information storage. And we wanted to use light and to switch between two states in the molecule. And then suddenly we discovered that besides switching, we could also make a movement that continued in one direction. And that was the start of our rotary motors. And once you have built a rotary motor, then you know you can control motion at that nanoscale, because our motors are only 1 nanometer, 1 billionth of a meter in size. And so once you can control motion, you can think about all kinds of dynamic functions, like movement, like transporters, like tiny machinery. So it started all with switches. A simple idea, 0-1 switch.
Simple ideas are the best ones. So I think that was the last question. So thank you very much, Professor Feringa, for being with us at the press conference. And I hope to see you here in December again.
Thank you so much. Thank you. It was my pleasure.
Bye-bye for now.
Bye-bye. Thank you.
Are there any questions to the panel before we close? We seem to be running out of time, but if there are any quick questions to the panelists. If not, we'll close this first part of the press conference. I know that several of you have requested interviews with experts from the Nobel Committee, and they will continue shortly. So thank you very much for your interest and in the Nobel Prize. Thanks. Bye.